Okay, good afternoon, 61C. Good afternoon. It's spring break next week. You should be happier. And we didn't assign you any homework over the break. Okay, so we're going to switch topics today. And actually, in today's lecture, we're going to cover two different things. I want to talk a bit about performance and what we mean by performance when we talk about computers. And then I want to, the second half of the lecture, talk about floating point, which is one of the important functional units on current processors. So what is performance? Right? When you're measuring performance in computer speak, there's usually two different measures you're interested in. One is latency. And latency is the time it takes to finish one thing. So from start to finish of a single task, how long does that take? Right, and that's measured in time, seconds. The other measure you're interested in performance is throughput, which is how many things per unit time do you actually manage to complete. So tasks completed per unit time is throughput. And some systems can have lower latency but lower throughput. Some systems can have higher latency but higher throughput. And why latency is important, this is just one example, thinking about very big systems, data center, cloud servers. There was an interesting experiment that was run, and this was done by Microsoft using their Bing search server. And what they're showing here is, what the researchers did here was take Bing as it normally works, but then artificially add a delay to increase the latency of search responses to Bing. And so when they added this amount of delay to responses for the server, this was the extra time between the user getting the response back and doing the next click. So notice it's not linear. Like if I add 200 milliseconds to response delay, it doesn't take the user an extra 200, it takes them 500 or more. And what's really going on there is people lose interest and phase out before they remember what they're going to click again for next, right? And also, the number of queries per user goes down, user satisfaction takes a dive, and most importantly, the money they make from ads and so on drops. And actually, when they were doing this experiment, after a little while, they realized, wait a minute, we're losing too much money. They stopped the experiment because it was costing them too much, right? So you might think it doesn't matter, but at the grand scale, you're aggregating all these users and all that ad revenue. Every time you're slowing them down, that's money that you could otherwise have got. So they actually cancel the experiment because the longer the delay, the fewer the user clicks. And part of it is this thing about you lose attention and wander off somewhere else on the web. So latency really matters. This application responsiveness is very important to end users. And it's non-linear is one thing people forget. So a slight increase in delay, you get distracted. Like humans are very bad at multitasking, like all you guys with your laptops open, checking your Facebook feeds, or watching soccer or whatever else you do with your laptops up. Very bad at multitasking. So a small increase in latency, if it disturbs your train of thought, you can become very unproductive. Just like when you're multitasking, you become ridiculously unproductive. So when you talk about CPU performance, you'll often hear people say, this thing is faster than that thing. And what do we mean by faster than? So this is getting at latency versus throughput. So if you have like a Ferrari, there's a Ferrari, I don't know cars, these must be one of Dave's lives, Ferrari 599 GTB, 2 passengers, but 11 seconds in a quarter mile, right? If you get an old school bus, you might think, it's kind of slow, but it can carry 54 passengers at once, right? So much higher throughput. But what about its quarter mile time? So let's take a look. Quarter mile time of a school bus. Hopefully this will work. Oops. I can see it. You guys can't see it. Why isn't that working? School bus, not very fast yet. There we go. There you go. All right. So when you're thinking high-performance servers, that's what you should have in mind. And actually, I think it's 12 seconds, the quarter-mile time on that thing. So not much slower than the Ferrari. Hopefully it'll go away now. See, that's the advertising. What's the next thing I should be interested in? All right. Okay. So latency is equivalent to that time to travel, quarter mile, and bandwidth is how many people you're transporting per second across that distance, right? So when we talk about defining relative CPU performance, the thing to remember about performance, ultimately, it all comes down to time. How long does it take to do something, right? And so when we say about performance, we usually think something performs better if it takes less time. So it's 1 over the execution time is how you should think about performance. So running on system X, the performance of X is 1 over the execution time on system X. And when you're comparing two machines, you say the performance on system X is better than the performance on system Y if the execution time on X is less than the execution time on Y, or 1 over the execution time is bigger, right? And you say one computer is n times faster than another if the ratio of the execution times is n. So I'm twice as fast if I take half as long to run the same thing. So that's the definition we use for faster than. You'll see some other definitions, but that's the one we use. It's the ratio of the execution times. So the bus takes 12 seconds versus 11.1 for the Ferrari. So the Ferrari's 1.08 times faster than the bus in that case. Special kind of bus, but there you go. Now, when you're measuring CPU performance, there's this clock you're all very aware of by now that ticks away and counts out the little steps you take in executing programs. And that tells you when things happen in the hardware. So the clock is a signal that synchronizes all the circuitry. And it has these discrete ticks, and those are called clock cycles or ticks or clock ticks, clock periods. And the clock frequency is just the inverse. How many of those ticks do you get per second? And like we already talked about in the class, the clock cycle time is just the reciprocal of a clock rate. So 3 gigahertz clock rate means you have a clock cycle time of 333 picoseconds, or 0.3, a third of a nanosecond, right? Now, we're focusing here on the CPU performance. When you have a whole system, it's not just the CPU, it's all the I/O, like your disk drives, your screen, your network, all those other things factor in. But if we just focus on the CPU for now and the code that runs on the CPU, when we think about the time it takes for the CPU to run a program, we could divide that into the clock cycles to run the program, multiplied by the time for each clock cycle, right? So if you have the third of a nanosecond is your clock cycle, well, how many clock cycles does it take to run the whole program? You can flip that around if you want, but think of it as clock cycles per program multiplied by the clock cycle time, right? That's the time for the whole program to run. Now, we can break it down even further. So the number of clock cycles to run the program depends on how many instructions you run, right? But also on how many clock cycles each instruction takes to execute, right? So you break this down further and say, well, the clock cycles per program is the number of instructions I have to execute to complete the program. And this is what we call a dynamic instruction count. Not how many instructions live in the memory of the machine, but how many instructions did I fetch and actually execute dynamically. So every time around the loop, I'm going to count all those instructions once again, right? It's not the number of unique instructions, the number of instructions I execute to finish the program. That number of instructions per program multiplied by the average number of clock cycles per instruction. So how many clock cycles does it take to do each instruction on average? And then again multiplied by the clock cycle time. So this is actually a very important breakdown way of thinking about CPU performance. And it's actually so important, it's actually got a name. This is called the iron law of computer performance, the iron law. Instructions per program times average clock cycles per instruction times clock cycle time. So instructions per program, we also call that the instruction count. How many instructions did you need to complete the task? The second term is clock cycles per instruction. And the computer architects abbreviate this to CPI, which just means cycles per instruction, right? CPI. Sometimes you'll hear of IPC, which is instructions per cycle, when you're working in a superscalar machine that can actually do more than one instruction per cycle. But in our world, where we have one instruction at a time, there's usually some extra stalls, and so then it's instructions per cycle. The third term is just the clock cycle time, which is just 1 over the clock rate in terms of frequency, right? So these three components are a very important way of breaking down how long it takes to run a program. So the overall goal is how much time does it take to run a program. This is another way of writing it out. So time is seconds per program. Time for the program is seconds for the program. And the units here are those components: instructions per program, clock cycles per instruction, and seconds per clock cycle. So you then see these cancel out and these cancel out, and you're left with seconds per program. All right, so this is the iron law way of breaking it down. Okay, so now the reason it's important architects break things down this way, it's useful to figure out different parts of your system have different impacts on these three components. And so let's go take a look at this. So for each of these components, let's sit and answer questions about which of these three timing components does this component affect. So this is part of your system: the algorithm, programming language, compiler, the instruction set architecture. Which components does each of these affect? Okay. Right, so what about the algorithm? Do you think the algorithm affects the instruction count? Yep. One answer? Sorry, you repeat that again? I didn't quite hear.
I mean, if you have effective algorithm, that means you can save space for a better data structure so that it can reduce the structure.
Okay, so if you have a better algorithm, it can save space. So you have a better data structure. What's another?
It reduces the instruction count because you use less instructions. You have to.
Right, so to fix an algorithm, you should use less instructions, right, to complete something. So if you do a quick sort versus a bubble sort, you're going to dynamically execute fewer instructions, right? So the algorithm is going to reduce the instruction count, right? How about cycles per instruction? Will a different algorithm change the cycles per instruction? No. So we think it's pretty fixed. So the algorithm is not going to change the cycles per instruction. So what affects the cycles per instruction? So what kind of instruction? Right, so the comment here as well, what kind of instruction? If it's a memory instruction, and you do lots of reads and writes, it may take longer. Why might a memory instruction take a long time? What did we just talk about last few lectures? Caches. What happens if you get a cache miss? Takes a long time. And so that instruction, the cycles for that one instruction are going to be a lot longer. So on average, if a lot of your memory instructions are missing a lot, your CPI is going to rise, right? So instead of taking one clock cycle, it's going to take one clock plus AMAT, right? And that could be a very long time. So question?
So you said that algorithm doesn't change CPI?
I haven't said anything about it yet. I'm just working through the background. So instructions have variable CPI depending on things like cache misses. So if I take a cache miss, that instruction is going to take many more cycles. And on average, that might raise the whole program's CPI if a lot of the memory instructions of the program are getting a lot of cache misses. So if I change the algorithm, can I affect the CPI? Yes. Right, yes, because I can change how many cache misses I get by changing the algorithm. Right. How about clock rate? Change the algorithm, change the clock rate. Any thoughts? No. Why not? Well, it's set by the hardware, right? The hardware said this is the clock frequency. So that's correct. That's a correct answer. A little caveat that these days it's not quite true, because how fast you run influences how much power the CPU takes. How much power the CPU takes influences how hot it gets. And if it gets too hot these days, it will slow down to reduce power. So in your laptops, when the fan starts whirring and the base of the case is really hot, the CPU is probably starting to run slower. And if you notice, all the Intel processors are sold with, 3 gigahertz and turbo boost up to 4 gigahertz. That turbo boost you'll only get if you kind of put it in a fridge and leave it alone, or blow on it really hard. You only hit those high clock rates if environment allows. But for the purpose of this class, just assume that the clock rate is fixed, so you're not changing it. But in reality, there is some impact. But it's really hard to understand between the program you're running, the power it consumes, the temperature it causes. When the temperature rises, the machine will cool it down partly by slowing down the clock rate on the processor. Okay. Cool. Programming language. What's that going to affect? So if I write in Python or write in C, is that going to change the instruction count for the program? Right, so they have a different way of turning your code into, your high-level programming language code into instructions. Whether it's interpreted or compiled, you have a big difference in instruction count. How about CPI? How's the programming language going to affect the CPI? Yep.
It's like each instruction, well, I'm assuming if it's like, instruction could be like a pseudo instruction, so like break it down, like the programming language, like put more instructions.
Yeah, but in general, if you write in 2 different programming languages, the actual instructions are executed quite different. Like we just said, it's going to affect the instruction count, and the mix of instructions is probably quite different. And that mix is going to change the average CPI, right? So you may have more or less loads of stores, or more or less other kinds of instructions or branches, depending on whether you're doing an interpreted language or doing a compiled language. So yeah, it's going to affect the CPI by changing the instruction mix that you run, right? If the mix of instructions changes, the CPI is going to change. How about clock rate? Is programming language going to change your clock rate? No, right? For the same reason we talked about for algorithm, it's fixed in the hardware. The programming language is not going to change things. Okay, how about the compiler? So say you're writing in C, but now you have C compiler A and C compiler B. Is that going to change your instruction count? Yes, right? So one compiler might be better at optimizing your code and taking instructions out. The other compiler may be not so good, and so you have less optimized code coming out of it, right? So the compiler can definitely change the instruction count. And what about CPI? Same thing, right? So same reasoning. If you change the instruction mix, you're likely going to change the CPI by some amount. And again, because this is just software, you're probably not going to change the clock rate. Okay, what about the instruction set architecture? So what if I change my design from using MIPS to using ARM or to using RISC-V? If I change, or x86, if I change the instruction set architecture, what's that going to change? Is that going to change the instruction count? Yeah, you're using different instructions. So even with the same base compiler generating code for 2 different architectures, you're going to get very different instruction counts. What about CPI? Yep, you expect that to change also, right? It's a very different instruction mix. And how about clock rate? Probably, yeah. So different ISAs, depending on your implementation style, they're probably going to result in different clock rates too. You have different hardware to run different ISAs. So pretty much, everything can affect these different factors in different ways. Instruction count, CPI, clock rate. Okay, quick clicker question. All right, so 2 machines, same clock, same instruction set, different clock cycle times, different CPIs. Which statement is true? Okay. So, there's a winner, but there's a few significant fraction of the class picked some other numbers too. So which one's correct? Okay, I'll give you one more minute. Change your mind. Talk to your neighbors and change your mind. Okay, so it looks like everybody switched to the big one, right? Yeah, so A is correct. So, 250 picoseconds, CPI of 2. So if you multiply, they both have the same instruction set. What that means is the instructions per program are going to be the same, right? So cycle time multiplied by CPI. So 250 picoseconds times 2. So on average, each instruction will take 500 picoseconds, and this guy's cycle time is 500 picoseconds. The CPI is a further 1.2, so it's just 1.2 times. Computer A is 1.2 times faster than computer B. Okay, when we're measuring performance, a really important thing is what is the computer doing when we're measuring performance, right? Most computers are very good at doing nothing really quickly, so that's not what you want to measure it doing. You want to measure it running something, right? And what do you measure it running? So we have what we call a workload, and that's a mixture of programs that are meant to represent the typical use case for that kind of computer system. And different computer systems have different workloads. So a data center server at Google runs very different apps than your iPhone, right? Very different mix of programs, different metrics. So for every kind of computer system, you want to figure out what's the typical workload, build a mix of those, and use those to evaluate your design decisions, or if you're purchasing computers, use them to evaluate products you want to buy. So you have to come up with some workload, and this means not only the programs, but also the input to the program. So, for example, if you want to evaluate how fast web browsers run, you need to have some pages for the web browser to render as well. You need to define those. And also, usually you want to run on a mix of things, because behavior in one program is usually not a very good predictor of a second program, so you need to build up enough programs that across the whole mix of programs, it kind of matches the kind of workload you imagine using the machine for. And then you want to weight it by how important each of those different components are to give an overall number. So the workload, it's the terminology. Workload is the thing that actually runs on your machine, and a benchmark is an approximation of that workload. And usually when people are competing in industry, you want to form some standard benchmark suite that people can all run the same way, and then they can compete against each other selling machines to end users. And also internally at the companies, if a benchmark is the main metric by which your customers buy machines, internally at the company as an architect, you're using that benchmark suite to optimize your machines, because that's what your end goal is, right? And one of the examples of doing this in industry is something called SPEC, and this is an organization stands for the System Performance Evaluation Cooperative, and this started in 1989. And this was a lot of the different desktop workstation vendors at the time came together to come up with a standard set of benchmarks they could all agree on that would be used to evaluate how fast their machines run, right? And they did several versions. So there was one in 89, one in 92, one in 95, one in 2000. But the last one was only released in 2006. And since then, they haven't released another one. They keep saying they're going to do another one, but they haven't quite got around to it yet. But anyway, what's known as Spec CPU 2006 is a benchmark suite. It contains 12 integer programs and 17 floating point programs. And by that I mean there's 12 programs that are predominantly integer code. They don't really use floating point. And the other programs are more floating point number crunching. They use a lot of floating point. We'll talk about floating point later today. So it's a mix of different kinds of program. And people like to turn this collection of benchmarks into a single number that will tell you whether one machine is faster than another. So people like simplicity in their decision making in their lives. They just want one number so they can easily say whether one is better than the other. Reality, performance is multidimensional, so some machines are better at some things and some machines are better at other things. In the spec world, the way they get a number is they take the execution time on an old reference computer. So they picked a single computer as the reference machine for spec, ran all the programs once on that, said how long it took on that reference machine, and then when you come up with a new machine, you run it on your new machine. Hopefully the execution time is faster than the reference machine. So you divide the time on the old machine by the time on the new machine, and that gives you a number which is how many times faster is your machine than the old machine, right? And everybody competes on this spec ratio, this number. So here's some numbers for, this is actually an older AMD chip, AMD Barcelona. So what this is telling you down here are the different benchmarks and what they are. Like one of them, for example, is the GNU C compiler. Another one is a Go playing game, chess playing game, quantum computer simulation, video compression. These are all things that, quantum simulation, that's something you all do regularly on your laptops, right? So that's why it's in here. Games, you might do a lot of that. Searching gene sequences, another thing you all do regularly on your laptops or iPhones, right? One thing to realize, part of the constraints they have is the codes have to be open source so they can distribute them as a benchmark. And they try to pick things that have different behaviors, but they're not necessarily exactly what any given user would run on their machine. But they hope if they have enough of these, they'll capture all the interesting behaviors. So this tells you the instruction count. So these run for quite a way, like several trillion instructions. This is in billions, so several trillion instructions total. This is the CPI on this machine. So running on this machine, you can see that the cycles per instruction varies a lot from less than 1 cycle per instruction. How does that happen? It takes less than 1 cycle to execute an instruction. Pipelining would just give you shorter. It does have multiple cores, but these are numbers just for one thread running. Out of order execution would be one way that the instructions could happen out of order, but why would the CPI be less than 1? The cycles per instruction be less than 1. Some of the instructions, no, the comment was maybe some of the instructions aren't executed. So the CPI number is of the instructions that you're executed, what was the average cycles per instruction. So how can it be less than 1? Yep. Right, so it can actually execute more than 1 instruction per cycle from a single thread. So from one program on 1 cycle, it can actually do more than 1 instruction at a time. And on average, that means you can get below 1 cycle per instruction. So a single thread on 1 core can do multiple instructions at the same time. That's one of the forms of parallelism machines take advantage of these days. So CPI goes from, sort of low of 0.75, but up to as much as nearly 3, right? So this is a machine that can do, I think, 3 or 4 instructions per cycle, but in this case, it's taken 3 cycles to do 1 instruction. And everything runs at the same clock rate. And what this is showing you is the execution time on this machine, the execution time on the reference machine, which is much slower. And the spec ratio is just this divided by that. So it just tells you how many times faster this new machine is than the reference machine. And this is your spec ratio. So this is kind of a speed-up number. So this is roughly 10, 20 times faster than the old reference machine they had, right? And that was probably the reference machine was probably 5, 10 years older than this machine we're trying out. Okay, so I'll just give you some idea of what spec int numbers look like. Actually, one I should point out, this guy. Look at this guy. Cycles per instruction, 10 cycles per instruction. What is up with that program? What is happening, do you think? What could possibly take 10 cycles per instruction? Yep. Right, it's a program that goes out to memory a lot, and so it's missing in the caches a lot, and so basically the processor is mostly just sitting there waiting for the memory system, right? So caches usually work, and you can see that from these numbers. They're pretty good, but occasionally you hit a workload where it's not so good. But even then, 10 cycles per instruction, that's not bad if you consider memory on this machine is probably 200 to 300 cycles away, right? And it's still managing to make progress, 10 cycles per instruction. That's still a lot better than you might imagine. Okay. Here's another clicker question. This is a great question. I'll give you two systems, A and B. Okay? I have to explain this a little first. So this is system A, this is system B. This is how fast it runs task 1. This is a rate number now. So these are both rates. So these are tasks per unit time. So this guy completes 10 tasks per unit time. This guy completes 20 tasks per unit time on task 1. On task 2, it's the other way around. This does 20 tasks per unit time. This one does 10 tasks per unit time. So, which system is faster? I'll give you just 1 minute on this. So which system is faster? System A, System B, they have the same performance, or it's unanswerable? Okay, so what do people think? Yep. Well, most people thought you can't really answer this question, right? That's kind of right. Yeah, this multidimensional space, you can't really say one is faster than the other. And the real answer is it depends who's selling the machines, right? This is interesting. So you can always lie with benchmark numbers. So if I just average the throughput across these two tasks, I'll say, well, they both get 15, things done per unit time on average. But if I want to sell one of the machines, I'll say, okay, let's take the throughput relative to B. So, okay, so A runs this 0.5 times as fast as B. And in this case, we're at twice as fast as B. I'll then average these, and look, that's 1.25. This guy's obviously better, right? Or I can say, maybe I'm trying to sell B. I'll say, let's take the measurement relative to that old system A you had. Well, I can run twice as fast on this task. I might be half as fast on here, but when I average it, I'm 25% 25% better, right? So you can see taking those ratios and averaging them, you kind of need to average in some way. You have multiple different tasks. You need different tasks to explain, different parts of your workload. Somehow you need to aggregate all those results in some way that makes sense. And this kind of simple averaging doesn't really seem to work, because you can exploit it any way you want. You get different answers, right? And so the folks who built the spec suite, they realized this was an issue. And the way they solved it was to take the geometric mean of the ratios, right? So all of the individual benchmarks, you divide the old machine's runtime by the new machine's runtime, and that gives you some speed up on each of the individual benchmarks. You take all those ratios, you multiply them all together and take the nth root. If you have n benchmarks, multiply them together, product of n things, and take the nth root. That's a geometric mean. And the one good thing about the geometric mean, it gives you the same relative answer regardless of which machine you pick as the reference, right? So it's really hard to cheat by picking one of the other machines as a reference. Now, one thing is it's not completely clear this is a better mean than any others. It just has this one property that it doesn't matter what you pick as a reference. You always get the same answer, the same relative answer. Okay, but that's what spec does. So the spec ratio, the single number you report, is gathered this way. So you start off with this, multiply all these numbers together and take the nth root of them to get the global average. Okay, so that's spec. So let's do a bit of administrivia. This is really the same as last time. So Project 2, Part 2, due on Sunday. Nothing assigned over spring break. The next assignment will be due April 5th. And notice we removed one assignment from the schedule. So we used to have a homework 5, homework 6 that would combine into one homework 5. So one less homework. Midterm is April 9th. Email us with conflicts. And we'll send you email about DSP accommodations. Okay. So actually, let's take a 2-minute break here. So we're going to switch topics. Let's take a break for now. Okay, let's get going again. So in the second half of class today, I want to switch completely and talk about floating point arithmetic. So far in our machines, we've only been looking at integer numbers in number representations and talked about how to add integers, signed and unsigned integers. But now we're going to start talking about floating point. And I'll start off with this quote of the day from Jim Gosling, who's one of the inventors of Java. 95% of the folks out there are completely clueless about floating point. I found this in the slide deck I inherited. I thought this was really funny because a lot of the people who work in floating point say a lot about Java's floating point design, which is actually really broken if you care about floating point. But yeah, a lot of people don't really understand floating point arithmetic, including the inventors of Java. So it's, on the one hand, an extremely complicated area. On the other hand, as a computer architect, thankfully, thanks to people here, the floating point standard has evolved to be one that's used everywhere the same, and so it's relatively easy to understand what that particular standard is, and we'll focus on that. What is floating point? So, computers are made to deal with numbers, also symbols, but everything inside the computer is just a collection of bits. And the different units that we build inside the computer, we just build them to interpret those bits in different ways. So the same set of bits could be an instruction, they could be a signed integer, they could be an unsigned integer, they could be a string of characters. It's just depending how you interpret those bits. If you have n bits, you can represent 2 to the n different things, different combinations of bits. We've already looked at unsigned integers, right? So you can have values from 0 to 2 to the n minus 1, right? So in 32 bits, you go all the way up to this big number, 4 billion. Or you can use the top bit as a signed bit and treat it as 2's complement number, in which case you get this range that you can represent using those same set of bits. plus or minus 2 billion or so. That's the range you get if you treat that set of bits as a signed integer, okay? But when we're dealing with programs working with data in the real world, there's often other kinds of numbers we need to deal with, not just integers. So things like, how many seconds are there in a millennium? That's quite a lot, 3 times 10 to the 10, right? Or very small numbers, the radius of atomic particles, you're down at 10 to the minus 11, right? These are very tiny numbers. And also you get numbers that are both, have integer and fractional, like 1.5. So how are you going to represent 1.5 inside the computer? Well, there's sort of easier way into this. Let's just start thinking about those small numbers or numbers that are around 1, with small fractional components, just small integers with some fractional component. So when you write these numbers out in decimal, you have what's called a decimal point. And that tells you the place at which you start dividing by 10 instead of multiplying by 10 as you move to the left or right, okay? So the same is true in binary. You can have a binary point which sits to the right of the least significant integer bit in your number, right? So I can do a binary representation like this, 10.1010. So this is a binary number with a binary point at this location, right? Now, a simple case, let's just assume you have a standard that says where the binary point is. So let's say that all our numbers, the binary point sits here, like 2 positions from the left, right? In that case, you could represent numbers that were almost as big as 4, right? 1 is 3.11111 is almost 4, right? Or all the way down to 0. Let's just assume we're dealing with unsigned numbers for now. So if we had this format with a fixed binary point, you'd have 10.1010, and the way you would turn this into a decimal number is just by multiplying each bit position by its weight. So you already know that this guy has weight 2, this guy has weight 1, so it's 1 times 2 to the 1, plus there's a 0 there. As you move to the other side of the binary point, the weight is divided down by 2, so this will be a half. The weight of this guy is a half, the weight of this is a quarter, this is an eighth, this is a 16th. So every position you move to the right of the binary point, things go down by a factor of 2. Just as the same way in decimal, when you write out a fraction, each digit to the right of the decimal point goes down by a factor of 10 in significance, right? So you just accumulate these bits by the weight, and that gives you the way of converting this to decimal. So this is 2.625 in decimal expressed as a binary number with a fixed position of the binary point. Okay, so, yep, question? Sorry, you have to speak up, I can't hear you. Yeah, that's right. So there's only a very limited set of numbers you can represent with this representation. It can only handle a few numbers and you're right, that the value of this bit is a 16th. So I can only increment by a 16th, and there's only a finite set of numbers I can represent in this format, right? The other thing to realize, in this format, we're not actually storing the point anywhere, right? It's just implied by our representation. We're saying, I'm going to interpret this set of 6 bits as being a number with a binary point after the second digit at the top. But that binary point is just implied. It's just our way of looking at this set of bits. We're going to look at, this is just to get going, right? Just the idea of a binary point. So if you look at the fractional powers of 2, they kind of look like this. So, 2 to the minus I. So these are the weights you assign as you go further and further from the binary point, right? So these numbers get smaller and smaller and smaller, basically just half, a quarter, 8th, 16th, 32nd, right? So just by weighting this by the bits, you can convert from fractional binary back to decimal. Just to sort of complete this, so adding adding is very easy. It's just like regular addition. In fact, you would use the same adder circuit as we'd use for integers. The binary point is just implied. So if you're adding 2 numbers with the same binary point, it's just like adding integers. You just add these together, and the result works out. When you do multiplies, it's a little bit more complicated. just as when you multiply decimal numbers with a decimal point in, you can just take the digits and multiply those out to get the correct string of digits. The extra bit of work you have to do is figure out where does the point live in the result, in product, right? So in adds, it's easy because it lives in the same place, but in multiplies, you have to figure out where the binary point is. And basically, there's 2 digits to the left here, 2 to the left there. So you'll end up with 4 digits to the left here in general. So the binary point will live there. So you just have to keep track of how the binary point moves as you're multiplying numbers, right? Remember, when you multiply 2 n-bit numbers together, you get a 2 n-bit result, right? There's a much wider range of outputs than there is of the size of the inputs. Okay. Now, floating point is called floating point because we don't just fix the binary point, right? We don't just have a representation. There are a few applications where you might have a fixed binary point representation. Some signal processing does that. But for general use, we use a floating point representation, which is called floating point because the point floats around. Okay? And the idea is to make the best use of the bits in your registers by only capturing the significant bits of the result. Okay, so say you had this number to keep in a register. Like all these bits here are all 0. All the bits here are 0 maybe. But you only really care about where there are significant bits that are not 0. And if you fix the binary point, you might find that, well, I have to chop off some of these bits because I spent some of this fixed format forces me to spend some bits holding those zeros that I don't really care about. So I just want to kind of align my storage to where the significant bits are in that binary string. Right, so try and do the best. The way we're going to do that is look for the most significant bit that's a 1, and make sure from there and onwards, that's the bits that we store in the register, right? And so you can let the binary point float around so that you'll align the useful bits into the storage you're using to represent the number. So we have to, once we have those bits that represent the number, it's not enough just to hold the 10101 pattern here. But you also have to remember where those live relative to the binary point. And that's done by storing a separate field called the exponent. And the exponent tells you, as in scientific notation, how much to shift up and down the binary bits you have to represent the correct value. Okay? So you should be familiar with this with scientific notation. Okay, so in scientific notation, you have the mantissa here with a decimal. This is in decimal with a decimal point. So 6.02 in decimal, multiplied by 10 to the 23. So you have this base here, which is the radix. So in scientific notation, we use decimal. So we use 10 as the radix. And that tells you how many decimal digits to shift the answer up and down. And then we have the exponent that gives you the shift amount. And we always write scientific notation in a normalized form with no leading zeros, okay? So if you write this number down, 1 billionth, in scientific notation, we write that as 1 times 10 to the minus 9, right? You could write it as 0.1 times 10 to the minus 8 or 10 times 10 to the minus 10, but those aren't normalized. And so by convention, you normalize them to have a single digit to the left of the decimal point and all the other digits to the right of the decimal point, and then you adjust the exponent correctly. Okay, that's just standard scientific notation. So we do the same kind of thing in our internal binary floating point representation, and one trick is to always keep the results normalized to maximize the useful digits we're storing in the word. So in binary, the equivalent is you have a binary mantissa with a binary point, and the radix now is 2, and the exponent is in, how many bit positions do I shift up and down to align this number correctly, to align the mantissa correctly. And so now this exponent allows this binary point to effectively shift up and down the number scale so that you can capture just the important, significant bits of the value you're trying to represent, right? That's the idea. So in C, in the C programming language, you can specify a variable as a floating point type by using the keyword float. and that'll give you a single precision value. In most systems, that'll be a 32-bit single precision floating point number. We'll go over the format of that in a minute. Or you can use double in C, and a double keyword will give you a double precision floating point number that occupies 64 bits of storage. Okay, how much if you need a more precise number. Okay, so that's how you access this through the C language. So let's take a look at the 32-bit representation that's pretty much standard on machines now. So we're going to represent numbers in this normalized format where there's a binary mantissa and then an exponent. And the way this is stored is like this. So this is the most significant bit, least significant bit, if you were treating this as an integer. Right? And the way we're going to store this is put the mantissa, which is called the significand, in the low 23 bits, the exponent in the next 8 bits, and the sign right at the top in 1 bit. Now, you need to represent positive and negative numbers, and in the floating point format, we do that using what's called the sign and magnitude representation. So we taught you unsigned integers, and then we also taught you 2's complement to represent signed integers. An alternative way to represent signed numbers is as a magnitude and then a separate sign. And that's what's used in the floating point format. So this is always unsigned, and then this is the actual sign bit. Okay, so this is the layout. 1 bit for the sign, 8 bits for the exponent, 23 bits for the significand. And in single precision, you can represent quite a large range, everything from 2 to the 38 down to 2 to the minus 38. Right, it's quite a large range of values. So, but it is a finite it's a finite range of values. Okay, so if you exceed the exponent, it won't be representable in this format, and so you get what's called overflow. Right, the number is just too big to fit in a number representation. Also in floating point, you can actually get what's called underflow. The number might be too small. So we can only take the exponent down to minus 38. And if your number is smaller than that, we just can't represent it. And so it underflows, and we just call it 0. Right? We just lost all the precision at that low end of the scale. Okay, so that's called underflow. And if you draw the sort of real number axis along here, so if you lay out all numbers along here, real numbers, there's 0 in the middle, right? So you have positive numbers here, negative numbers here. The way to think about it, there's a representable range from pretty small numbers to pretty big numbers. If the number's bigger than this, it overflows. But if it's less than this number, it underflows. But we can represent 0, right? But in this small range in the middle, all these numbers are not representable. And also, if it's very negative and very large, it's also not representable, right? So there's just this piece of the number line that we can actually approximate using these floating point numbers. So there's actually a standard representation called IEEE 754. And prior to this standard becoming dominant, which happened in the late 70s, early 80s, every manufacturer had their own floating point format. Right? They had their own way of splitting things up into sign, exponent, mantissa, and so on. And that meant that if you wrote a program in a high-level language that used floating point, you would calculate expression on one machine, and you get completely different answers running it on another machine. And this used to drive the numerical analysts crazy because they were trying to write programs that would say invert a matrix. And it would just be stable on one machine and unstable on another. They'd have to special case for every single machine its floating point. And so there was a big effort that was led by Professor Kakan here at Berkeley to standardize this floating point format. And that resulted in this IEEE standard 754. And since that time, all machines basically have adopted this floating point format for their internal arithmetic. There's only a few people that really understand a floating point. Professor Kahan and his students were, we're centers of excellence here at Berkeley in floating point. And one of the things they did is carefully design this so it usually does what you want it to do, even if you don't really understand a floating point. The standard and the way the operations are defined usually does the right thing for you. So even if you don't understand a floating point, it usually does the right thing. And that was one of their big innovations. So in the IEEE format, there's this format of 1 bit plus 8 bits plus 23 bits for a single precision. The significand is in sign and magnitude format. And one trick is to get one more bit of precision out of that significand. You make this observation that if I have a binary number and I'm going to normalize it, so I'm always going to have 1 point, some fraction, in binary scientific notation. I don't need to hold the 1 because there's always a 1 at the front of all the numbers, right? So you don't have to hold the 1, so you take the significand, you add an extra bit at the front, and then that's what you align with the exponent, right? So because you always store the numbers in a normalized form, there's always going to be a 1 at the front because that's the most significant bit that you need to represent. You don't need to actually represent it because you know it's a 1. So it's implicit in the representation. That gives you 1 more bit. And another thing to say is just that the double precision version of this is just sort of bigger. So there's like 52 bits here and 11 bits here. And it can represent a really huge range of numbers at great precision. Okay. Now, I mentioned that the mantissa, the significand, is represented using sign magnitude notation. The exponent is represented in a different way. So exponent is represented actually using what's called a biased exponent notation. So you might remember on the midterm there was a question about biased number representations. One place that shows up is in the exponent encoding for these floating point numbers. So instead of these 8 bits being a signed or unsigned integer, there's actually a bias which is about halfway up. And so the negative exponents start at just above 0 at 1, and they count up to almost the biggest unsigned number. But it's treated as halfway through there is the 0 point. And the reason they did this is they wanted to, if you ignore the sign bit, they can compare the rest of the number as an integer. So if you want to see if 2 integer numbers are bigger or less than each other, this exponent and this significand, you can just treat this as a long integer and do an integer compare, and that will be a valid floating point magnitude compare as well. So it's like one little trick they did in the number representation. So basically this trick of using the bias thing makes the negative numbers look smaller than the positive numbers, right? Because you start at 0 is the most negative, and then you count up. Halfway through there you hit 0, then on the way up you hit the largest positive number. So the exponent is then ordered the same way as integers are ordered. Right, so in IEEE you have a bias of 127 for single precision. So 127 is exponent of 0 in that 8-bit field, and 1023 is the bias for double precision. So when you want to convert this number in IEEE format to a decimal number, scientific notation, it's -1 raised to the s bit. So basically -1 to the 0 is, what's -1 to the 0? 1, right? Positive 1. -1 to the 1 is -1, right? Either -1 or 1 multiplied by, you add this 1 bit here, the implied 1 bit, and then the significant bits, then multiply all of that by 2 raised to the exponent -127. This field, treat this is an unsigned integer, subtract 127, and that gives the exponent. Okay, so that's how you interpret these 32 bits as a floating point number. Okay. So double precision is almost the same, just the fields are bigger and the exponent is also, the bias is larger for the exponent. There's also a quadruple precision floating point that's also defined, which is 128 bits floating point numbers. Okay, and that's used in some applications that need very high accuracy. Though there's very few machines that have been built that actually support that in hardware. Whereas these days, the single precision, double precision, nearly every machine you buy has hardware support for those floating point operations. So the hardware just reads 32 bits in, or say it wants to add 32-bit numbers. It reads 2 32-bit numbers, interprets them as floating point, does the addition, calculates the significands, the exponents, and gives you the result in 32 bits on the output, all in hardware, right? So that's pretty standard today. So I mentioned Professor Kahan. He was really the father of the floating point standard, and for that he won the Turing Award in 1989. This was such an important accomplishment, just getting the industry to agree on how to represent numbers in computers. And the Turing Award, for those who don't know, it's like the Nobel Prize in computing, so very important. So it's part of your legacy here at Berkeley. I think there used to be 3 or 4 lectures on floating point in this class. We've managed to cut it down to half a lecture. So, Okay, so we just talked about the basics of it. Just to go into a bit more detail, I mentioned before that one of the things that Professor Kahan and his group and the other people working on this try to do is make floating point work right, even if you don't really know what you're doing. And one of the ideas in here is, in floating point, if you divide a number by 0, you might think, well, I just want this computer to crash. And it turns out that wouldn't actually be very useful. What's actually better is if you have a representation for infinity. So in the IEEE standard, you can encode infinity in 32 bits. That's a pretty cool trick, right? Infinite numbers represented in 32 bits. And actually, not only one infinity, you get two infinities. You get plus infinity, minus infinity, all encoded in 32 bits. Well, how do they do that? Well, they just reserved a particular encoding, and the idea is that your hardware can interpret infinity as a valid value for some further operations. So, for example, if I produce an infinity by, for example, dividing x by 0, it's still okay to compare that against another number, and that's a valid result. So x divided by 0 is probably greater than y, right? Unless y is also infinity, right? If y is a finite number, infinity is greater than that number, so the answer is true, right? X divided by, and so you can keep going without, you didn't need to crash the program in that case, right? You just return infinity for x divided by 0 and keep running. So the way this is represented is, remember that 8-bit exponent field, instead of using all of those for exponents, values of 0 and the maximum value, all ones, those are reserved to mean special kinds of number. Okay, and if you have the all ones in the exponent field with the significand all zeros, that represents an infinity, right? And so that's how it's actually encoded in the bit pattern you'll see in the machine. Okay, so the functional units that read operands and say the divide unit will read two numbers, figure out one of them 0, and produce the infinity representation on the output and just throw that back to a register. Okay, so just one of those encodings is reserved for that value, and the sign bit is there to let you have plus and minus infinity. Okay. Another interesting thing was, how do you represent 0 in this system? Remember, most of the floating point numbers, you look for the most significant bit that's a 1, and that's where you know the binary point should be, just to the right of that leading bit that's a 1. But if your value is 0, there are no leading bits. All your bits are 0. So how do you represent 0? Well, simple idea is just, well, the exponent, we have this value at 0 at the bottom end, we'll reserve that together with a significand of 0 to mean it's really 0. If the exponent field is 0, significant field is 0, this is a 0. The interesting thing is the sign bit is still there, because this is sign magnitude notation. And actually there are two zeros in IEEE standards, plus 0 and minus 0. And they're both valid representations of 0. And there are very subtle rules about what happens, what generates plus 0, what generates minus 0, and whether you can tell them apart. Yep. Sorry, say again. If your significand is all zeros and your exponent is not all zeros, that's 0. Okay, so the question was, what if your significand is zeros, but your exponent is something else? Well, that represents some power of 2. Because if your significand is all zeros and this is not, then that means it's a number that has a 1 implicitly here. So that 1 gets added onto those zeros, so it's 1 times 2 to the exponent minus 127, right? So it just if the significand is all zeros, it means it's some power of 2, either large integer power 2 or a fractional power 2. So there are some other special numbers. We talked about plus infinity and minus infinity. Let's take a look at what we defined so far. So if the exponent is 0, significand 0, that's a 0. If significand is 0 and the exponent is 255, all ones, then that's plus or minus infinity. In the middle are all the sort of regular numbers. 1 to 254, anything here means it's some kind of floating point number, right? But you notice there's a few things we haven't used yet in the encoding, a few slots in the encoding space we haven't used. So what are those going to be? So exponent of 0, non-zero, exponent of 255, and non-zero. So, Professor Gahan was pretty clever here. It's like, hey, we can do something with these extra number encodings. And the first one was actually having a way to represent something that wasn't a number. So an example would be if you take the square root of a negative number or divide 0 by 0, the answer is not infinity, that's not a valid thing to do. And so in the standard, the idea is instead of stopping the computation then, you would instead just represent the fact that this was not a number. And so one of the numbers you can represent is not a number. So, and we call this nans, N-A-Ns, not a number. And if you see strings printed out from your program sometimes, you see this N-A-N show up when you've done something wrong and there's in your floating point computation, right? So nan stands for not a number. And those are represented in the bit encoding as exponent of 255, all ones, and the significand being non-zero, right? Remember, if the exponent is 255 and the significand is 0, that's infinity. But if the significand is non-zero, that's a nan, and not a number. And the idea of these nans is they can help you with debugging. So they'll sort of propagate through, and you'll see the chain of nans going through your code as you debug it. But also sometimes you'll calculate something, get a nan, then later in your code you'll branch around it and not use it. So instead of crashing the machine, it's better just keep going, and maybe you don't actually need that value after all, right? You can just work around it. So the goal here is, for most of the floating point computations, instead of having lots of checks and inlining your code, the point of this floating point standard is let your code run normally most of the time and just kind of do the right thing with the values as they go by. So one thing is any operation, if you feed a nan into an operation, it makes the output be a nan as well. So if you add anything to a nan, the output is a nan, right, and so on. They just kind of propagate through your code. Okay. One idea that Professor Kahan had was that because you have those significant bits, anything that's non-zero is a nan. You can actually encode information in those bits to indicate where the nan was produced. But in practice, nobody does that because it'd be too hard to do in the hardware for lots of reasons. And so that hasn't been adopted. So most machines just have a fixed bit pattern they use for all the nans. Okay, so that's one of those holes in the representation, right? So this is where nans live. There's also this slot where exponent is 0 and the significand is non-zero. And the idea here is to deal with this problem that as numbers get too small, they underflow and drop off the bottom of the representable range, right? So we can represent 0 and we can represent infinities, but below the smallest number, between 0 and the smallest number, there's a gap in the numbers we can represent. And part of the problem here is we cannot use those significant bits because we had this normalization trick we were using. Remember, we started with the leading 1 bit and removed it because we didn't need to store it in the word. So that's a great idea, except that it means that if your exponent bottoms out at the smallest exponent, which is 1, right, it assumes there's a 1 bit there, and we cannot kind of use those bits lower down to hold data. And so the idea is, well, let's go make the exponent 0, and if the significand is non-zero, that represents what's called a denormalized number. So it's no longer normalized. There is no more implicit 1 bit, and the bits in the significand are actually the bits of that number. Okay, so that lets us get further down into these representable numbers. So that's the solution here. So you implement these denormalized numbers, so there's no implied leading 1. And so now you can, so when the exponent is 0, there's no leading 1, and the bits in the significand are those remaining bits, and so they're scaled by that exponent. And this lets you get smaller and smaller numbers. Yeah. So you're all happy now that you can represent those small numbers. So now that this is kind of filling out this table, summarizing it all, right? So now we kind of used all the different encodings to represent all these different kinds of numbers. Okay, I'll just kind of go back over this. So the reason we have floating point is it lets us represent all kinds of numbers. And remember, these are all approximations of real numbers, because all those floating point numbers have only a finite significant width, and you aren't going to truncate bits to the right of the significance. So you're not going to represent things exactly. And the tricks that the 754 standard encodes let you represent infinities, plus or minus infinities, also represent not-a numbers, and also uses the denormalize trick to get you back some of that small numbers. And what's amazing, this has really become a global standard. Everybody uses this in all their machines. Even some companies like IBM and Cray that had their own floating point standard in their hardware, and DEC actually in the VAX, they had their own floating point standards. When this standard came out, they actually changed their instruction set architecture to add more instructions to support this IEEE standard, because basically all the people that wrote numerical code insisted upon having this in their machines to make their life sane. And so everything uses this now. What's a little frustrating to people like Gahan is that the Java programming language, for example, restricts which pieces of the standard you could use and actually removes all of the nice features they added to help write numerical libraries. So that's why I found that quote from Jim Gosling a bit funny, because he's responsible for part of the problem there. Okay, so to wrap up, finish early because it's spring break, whatever. Instructions per program times clock cycles per instruction, seconds per clock cycle, that's the time it takes to run a program. Floating point numbers are approximations of real numbers in a finite number of bits. So have a good break, and I'll see you in a week's time.